Okay, so the Lorentz transformation. Even before we start, we know two things about this Lorentz transformation. Or more precisely, we have two requirements for how it should behave. For one thing, it should give an invariant speed of light in all reference systems. And the second requirement is that for velocities much smaller than the speed of light, it should reduce to the Galilei transformation. So these are the requirements, and we consider them a typical situation looking like follows. We have two inertial systems moving relative to each other with a velocity v, which is constant, and we take the movement without any loss of generality to be along the z-axis. And assume that we have chosen the initial conditions here so that the two inertial systems coincide. They have common origo at 0 time. So the Lorentz transformation when going from one set of coordinates to the other, in this case, looks like this. So what this tells us is that when this coordinate system is moving with a velocity v along the z-axis, the two perpendicular coordinates, two perpendicular axes remain unchanged. There is no transformation along the x or the y direction. However, the coordinate along the relative motion is transformed in the following way. And we see that there's an extra factor gamma compared to the Galilei transformation. And this gamma factor is defined in the following way, where beta is the ratio of this velocity relative to the speed of light. So there are at least three things which should be remarked about the Lorentz transformation. For one thing, the coordinates which are perpendicular to the motion are unchanged. The second thing is that the Galilei transformation differs by the introduction of this gamma factor. And thirdly, which is perhaps the most challenging aspect to grasp, at least intuitively, is that time itself is perceived differently in these two coordinate systems. So an observer here experiences time itself as different from time as experienced here. So this set of transformation equations tells us how to go from S to S prime. So we know all the coordinates x, y, z, t, and this tells us how to obtain the primed equivalents. Let's say now that we are in the opposite situation. We are located here, so we know all the coordinates here, all the primed coordinates, and we want to obtain this set of coordinates. So we're performing the inverse transformation. So given this set of transformation rules, how can we obtain the inverse transformation?
Changing the sign of the velocity.
Yeah, it's as simple as that. Because if we are positioned here, then we are observing this system. As we see it, this system is moving in the opposite direction with the same velocity. So we get the inverse transformation just by changing the sign of the velocity. An aspect of these transformation equations which we can certainly make use of is that they are linear. And we can make use of this because we developed an entire sort of formalism for these type of linear transformations back in chapter 4, I think. So we should be able to actually use many of the ideas from this type of rotational transformation business to these Lorentz transformations, because we also have here linear transformations. So let's see now, let's put these transformation equations to the test. Do they really respect the invariance of C? So consider the following scenario. Assume that we have a point source located precisely at the origo S prime, which emits a light front at time equals 0. What is the equation of motion for this light front? In other words, how does the position of the light front depend on time? Any ideas?
R equals C times T?
Yep. So for an observer in this prime system, the position of light front is simply its velocity constant, being constant multiplied with time. We can rewrite this by squaring it in the following way. now comes the test. If we now transform these coordinates back to the coordinate system in S, in other words, to find out how an observer in S sees that this light moves, what kind of speed do we obtain? Okay, so the first two terms are trivial. They're just the same. And then we use these transformations for C prime and T prime. So let me just add 0 to this right-hand side, z squared minus z squared, and then write out these squares here and here. I can rewrite this line as follows. So by multiplying now 1 here with 1 minus beta squared, both in the denominator and denominator, I see that I get 1 minus beta squared minus 1. So I'm left with only minus beta squared, which cancels this term. So this is 0. This is 0. And so I'm left with this. Which I can rewrite in the following way. So basically what we end up with here is the following equation, or this. So we see that the equation of motion for the wavefront as seen from the system S has exactly the same form as the equation of motion as seen from S prime, with the same speed for the wavefront. So this directly demonstrates that the Lorentz transformation satisfies the first of our requirements, the speed of light is invariant. So how about the second one? What happens if the velocity is much smaller than the speed of light? Well, in that case, beta is much smaller than 1. And we see that as v becomes very small, gamma goes towards 1. So in this limit, we should then get 1 here, so that the transformation for z prime is just a conventional Galilean transformation. And here, for the transformation of the time coordinate, we get 1 and then t. And then here, this term also vanishes as v goes to 0. V over c goes to 0. So we get t prime equals t. So we regain the Galilean transformation. So this set of equations and their belonging inverse transformation by reversing the velocity give us an invariant speed of light, and they reduce the Galilean transformation in the correct limit. So they seem to work out good so far. And I just, for convenience, chose one particular axis as the relative motion. But we can write these down in vector form for any arbitrary direction of S and S prime. So in vector form, where now you have a velocity in an arbitrary direction, the transformation equations look like this. And you can easily verify that in the special case where beta is along the z-axis, as we considered, this reduces to our set of transformations. Now, as I mentioned, due to the linearity, to the linear nature of these transformations, we should be able to use the concepts introduced in the previous chapter. In order to do so, we have to introduce a fourth dimension. And this might sound incredibly strange, but the fourth dimension is just time. So we consider 3 spatial dimensions and 1 time dimension. So the point is that whereas we are used to thinking of sort of space and time as separate things, in the special theory of relativity, we have to discard this notion. We have to think differently. We have to think of space-time, space, sort of that space and time intertwine each other. So it's a combination of them that tells us how different events take place. And this becomes important when the velocity is comparable to the speed of light. So we introduce a fourth dimension. The three first dimensions are x, y, and z, and the fourth dimension is I, c, t. I will comment a bit later on this particular choice. So what we have at hand here is a four-dimensional so-called Minkowski space. And although we cannot visualize it, since we can only visualize 3D, these are the axes of the system. So perhaps one way to think of this is that if you recall the configuration space that we dealt with when discussing Hamilton's principle, we had sort of n number of axes corresponding to each generalized coordinate describing the system. So we can have a multi-dimensional space which describes sort of the system, even though it's hard to visualize. So think of Minkowski space just as you have four axes, with three of them being space and the fourth time. So this quantity that we have calculated can now be expressed very conveniently in Minkowski space. Like this. And this x mu is known as a 4 vector. So we've used Einstein's sum convention here due to repeated indices, and to distinguish 4 vectors from our conventional 3 vectors that we use in spatial space, we have used a Greek index. So we use Roman indices for our standard 3 vectors in normal space, and we use Greek indices for these 4 vectors. So we can now very compactly express the invariance of the speed of light by saying that this x mu, the norm of this 4 vector, is a constant. So by saying that x mu is an invariant for all inertial systems, we're effectively saying that the speed of light is the same in all inertial systems. Because this form, as we saw, was invariant, regardless if we consider s or s prime. And we can express this in a different way. In other words, the norm of the position vector x mu in Minkowski space, which you can think of as a sort of a position vector in Minkowski space, is invariant under Lorentz transformation. And the reason for why I would like to highlight this is that it's completely analogous to what we considered when we dealt with the rotations. We thought a rotation would preserve the length of a position vector or any vector. So let me just briefly comment on this. Some of you may be accustomed to seeing this written as x lower index mu times x upper index mu. And this would be known as the product of a covariant and a contravariant for vector. Now, I will say more about this probably in the next lecture, where we discuss different choices of metric. So in this particular choice of metric, in other words, our choice for how these axes in Minkowski space should look like, the covariant and the contravariant vector are the same. And I do this just to eliminate any possible confusion between the upper and lower indices. Because if they're the same, well, then we can just use the lower index all the time. But I'll comment more on this later. Now, due to this statement, we can write the following. The Lorentz transformation is an orthogonal transformation in Minkowski space. So it's orthogonal because it preserves the norm. So let's try to take into account all of these ideas that we developed, sort of the formalism that we developed when dealing with the rotation of systems previously. So let's write this Lorentz transformation as a matrix equation, which means that we can write it like this. Or if you will, in component form. And let's consider the special case that the relative velocity is along the z-axis. by inspecting the set of equations that we wrote down, we can then identify the following matrix just by considering each element and how it couples to the coordinate. So we see that, for instance, we know that the perpendicular directions to the relative motion should remain unchanged. So x and y transform as identity, whereas z and time couple for this choice of the relative velocity. So it might be a useful exercise in order to also distinguish between these Greek and Roman indices, the 3 and the 4 vectors, to consider what does this transformation matrix look like in the case where we have an arbitrary motion, arbitrary relative motion. So I'll probably erase, no, we still have them there, okay. So then we should consider the following transformation equations. Which I now write in component form. So the first of these equations, r prime equals r plus the rest, correspond then to the first 3 coordinates. So I use a Roman index, xj prime. So we get the following. The product between beta and r are done in normal Cartesian space. So it's a product of 3 vectors. So it's beta k, xk with a sum convention. And then I've expressed time through x4 like this. And so the jth component of the upper equation is written like this. The lower equation is written like this. So again exchange time for x4 and then inserted the product between beta and r, which are both 3 vectors. So we use Roman indices. So we get, for instance, this transformation matrix element by considering this equation here. So we have delta jk, because we only have a contribution here if these two indices are the same. And then we have this contribution here. And we also have Lj4 is I gamma beta j. Okay, so then I have a challenge for you. Using these transformation equations, which now have been written in component form, what is L44? So the general 4 element, the element in the 4th row and 4th column, for an arbitrary transformation, arbitrary velocity. So what does L44 represent? If you were to put it into words. Well, L44 says something about the contribution of x4 to x4 prime. So we have our equation for x4 prime here. So then the question is, what is the coefficient in front of x4? So L44 is a gamma. This is the contribution from x4 to x4 prime. Do you see it? So to put this into words, for a general arbitrary relative motion, the position vector in Minkowski space in the prime system is a linear combination or superposition of all the coordinates in the unprime system. And this L matrix you can think of as the contribution from each of the old coordinates to the new coordinate. So along each row here, you find the coefficients in front of the possible contributions from the unprimed coordinates. Yes?
You said that the Lorentz transformation is an orthogonal transformation, but isn't it rather Hermitian?
Yeah, that's more general. You're right. So it's orthogonal, but it's also in fact something more general, as you say, it's Hermitian. Meaning that if you take the adjoint operator here, you complex conjugate it and also transpose it, you get the same. Yeah. So basically you can say that for real matrices, orthogonality is the same as hermiticity. Yeah. But this is a complex matrix. Okay, so for an orthogonal matrix, one of our main results was that the inverse of the matrix would be equal to its transpose. So the inverse Lorentz transformation should be written like this, where now the -1 here doesn't mean 1 over L mu nu, but it means the inverse transformation matrix. So due to this property we have the following. So from this we can immediately write down the inverse Lorentz transformation. Considering just for simplicity here the case where we have motion along the z-axis. So it's just a transpose. Does this result seem consistent with what we said previously about inverse Lorentz transformation.
Yeah, just flip the sign on V.
On the V.
So that changes the sign.
Exactly. So gamma here is invariant if you change V, because it depends on V squared. The only dependence on V, which is linear here, is in beta. So if you change the sign of V, you change beta, which is exactly what we've done here. So this is consistent with just changing the velocity. Right. I think it's a good point to stop there.